Hi, hi, hi. Okay, so we've been working with homomorphisms and we've been computing things about them. Today we're going to talk about the sort of correct scheme, the correct method that we're going to use to write down how to represent a linear transformation, a linear map, and homomorphism, and figure out sort of what's its effect on kind of arbitrary members of the domain. So we need a computational scheme that makes it easy to do the kinds of calculations that we're going to be doing. Before that, of course, we're going to do the check-in. The check-in goes back to the rank and the nullity and that kind of stuff. So it's kind of a quick one. Let's have a it's a reminder. Let's have a whack. So let's see. How do I do? I'm looking at the derivative map. So it's the derivative map from P3 to P2, from polyspace 3 to polyspace 2. And I expect that a person knows what the derivative map is, but even if you don't, it's simply this. A plus bx plus cx squared plus dx cubed is b plus 2c, I'm out of room, b plus 2c times x plus 3d times x squared. I could write plus 0x cubed, but maybe I'll stop doing that at this point. I hope that a person knows that I want to get a quadratic out because I'm interested in a quadratics as out. Okay, so I'm asked to find the null space, asked to find the nullity, and asked to find the rank. So the null space is the kind of stuff we've done lots of times before. The null space of the ddx map is it's the set of a plus bx plus cx squared plus dx cubed, where, let's see here, I need to have that b plus 2cx plus 3dx squared is 0, and that's, of course, the 0 polynomial in poly 2. So then that gives me the set of a plus bx plus cx squared plus dx cubed, where so to be the 0 polynomial, I need b equals 0. 2cx gives me 2x. Excuse me, gives me 0. So and 2c equals 0 and 3d equals 0. Ran out of room. It says and 3d equals 0. If you could only read it, it would say that. So basically, b equals 0, c equals 0, and d equals 0. And so I'm just simply looking at the constant polynomials, a times 1. I don't know how to make it sort of extra clear that this is meant to be the constant polynomials, where a is free. Okay, so basically what everybody knows is that when you take a derivative of a constant polynomial, you get 0. And if you take the derivative of a non-constant polynomial, you don't get 0. So 2, the nullity. The nullity is the dimension of the null space. So of course I already wrote in the basis there. The basis for the null space is I don't know at what length is it helpful to write it. So maybe I'll do the absolute silliest thing and write 0 plus 0. It's going to be 1 plus 0x plus 0x squared. Excuse me, plus 0x cubed. I don't know, that's way overkill, but anyway, I wrote it. So the nullity is 1. The dimension of that basis, the number of things in that basis is 1. The dimension of the null space is 1. Nullity is 1. Okay, and then for the rank, of course, we have the formula, and I'm determined to apply it. So we know that the dimension, oops, sorry, I spelled no wrong. Know that the dimension of the domain, which is the dimension of polyspace 3, is 4. There are 4 letters, 1, 2, 3, 4, A, B, C, D, so the dimension is 4. So that means that since rank plus nullity equals the dimension of the domain, so the rank is 3. Okay, so without computing the range space, I can find the dimension of the range space. The dimension of the range space, the rank is 3. So that rank plus nullity equals the dimension of the domain comes up a lot. Turns out to be a very convenient formula. Okay, good. So I'm ready to talk about what I want to talk about today. The scheme for computing with linear maps. So I have to introduce it. It involves basically writing out the parts and organizing them into some convenient form. The convenient form will prove to be a matrix. So I'm going to represent linear maps with matrices. So we've already seen the result that I hope I emphasized is key, that the action of a linear map is determined by its action on a basis. That if you know what h does to beta 1 through beta n, then you know what h does to any v. And we, of course, had a term for how do you get from the betas to v. We call that extending the action of the map linearly from the basis to the entire domain. So I'm going to introduce a scheme for the calculations, and it basically just involves using those c's. So I'm going to pick just an arbitrary domain space and an arbitrary codomain space, range space, and I have a basis for each of them, and I deliberately didn't pick the easiest basis because, as I've said a number of times before, sometimes the easy basis hides some things that you want to see. So if you pick kind of a generic kind of arbitrary thing, don't pick a killer, but pick something that's relatively messy. Sometimes you see things that you don't see if you go for the absolutely most straightforward thing. So here we go. I have a basis 1 plus x plus x squared. So I displayed the action of h on 1 plus x, and on 1 plus x squared. And again, I didn't make the result be easy. I tried to make it be kind of generic, not brutal, 8 decimal places kind of craziness, but instead not 0, 0, 0, 1, sort of relatively jumbled up numbers. Okay, relatively jumbled up, relatively generic numbers. And then I want to find, with this action, this is copied from the previous slide, with this action on the domain's basis, I'm going to represent 0, 1, 3, 2, and minus 2, minus 1 with respect to the output spaces. So remember the output, the range basis is 2, 0, minus 1, 1. So I'm going to represent 0, 1 with respect to w's basis. I'm going to represent 3, 2 with respect to w's basis. And I'm going to represent minus 2, minus 1 with respect to w's basis. So I'm getting numbers for all these things. And then I'm going to put the numbers in some organized form. It'll be in a matrix. And that'll be how we do the computation. So we wrote down the representation of 0, 1, the representation of 3, 2, and the representation of minus 2, minus 1. And I included the calculation if you want to remind yourself what does representation mean. So I represented 0, 1 with respect to the range spaces basis. I represented 3, 2 with respect to the range spaces basis. And I represented a minus 2, minus 1 with respect to the range spaces basis. And I got 6 different numbers: the 1/2, the 5/2, the minus 3/2, the 1, the 2, the minus 1. And they're just numbers. And again, I deliberately chose numbers that aren't pretty because sometimes you see more when the numbers are somehow generic. I'm going to summarize all the calculations I've done so far by writing these. I take this vector, I put it there. I take this vector, I put it there. I take beta 3's vector, and I put it in the third column. So you summarize the calculations I've done so far by putting those numbers down into some organized form, namely a matrix. 2 rows, 3 columns. I'm going to call that the matrix representation of H with respect to the starting and ending basis, BV and BW. And the point is to calculate the effect of the map on an arbitrary V from the domain. So you take an arbitrary V from the domain, and what exactly does H do to it? And you see at the bottom of this slide, to figure out what is the action of H on an arbitrary V, you find how to represent V with respect to the basis. You get a C1, a C2, and a C3. And then you take the numbers from the matrix. Remember the matrix? 1/2, 5/2, minus 3/2. There they are, 1/2, 5/2, minus 3/2. And you remember the matrix was 1, 2, minus 1. So there's the 1, 2, minus 1. Why is that again? Well, because if you want to figure out what h does to this vector v, what does h do to v? Well, the fact that h is a linear map means that the h of the combination is the combination of the h's. What is c times h of beta 1? Well, there you go. It's c1 times, there you go. We just saw on the previous slide that this is how you express h of beta 1. I used, of course, expressed it with respect to the output spaces basis. But anyway, this right here, this expression is a correct way to write down h of beta 1. This is a correct way to write down h of beta 2. This is a correct way to write down h of beta 3. And the c1 gets multiplied by the half and also by the 1. There it is. The c1 is multiplied by the half and also by the 1. The c2 gets multiplied by the 5 halves and also by the 2. The c2 gets multiplied by the 5 halves and also by the 2. And finally, the c3 gets multiplied by the minus 3 halves and the minus 1. And there's the c3 by those two numbers. So this, in short, is just simply the way that the numbers fall. 2, 0 gets multiplied by c1 times a half, c2 times 5 halves, c3 times minus 3 halves. That's what 2, 0 gets multiplied by when you break out the 2, 0. Minus 1, 1 gets multiplied by 1 and also by 2 and also by minus 1. That's simply that's just the way the numbers work out. They combine in this way. The combinatorics is just that. You end up multiplying 1 half times the c1, 5 halves times the c2, and minus 3 halves times the c3, and like that for the bottom line. So we're going to represent that by writing the matrix here, writing the column vector representation here, and we will define the combination of this matrix and this column to be you take the first thing in that row, combine it with the c1. Take the second thing in that row, combine it with the c2. Take the third thing in that row, combine it with the c3, and make that the first row of the result. That's the definition. And why do we define it that way? We defined it that way because that's the way the letters work out. That's just how they combine. When you do the distributive law and then factor out the 2, 0, that's just what you get. That's all. That's just how they combine. So that the definition of how do they combine is just what it was on the previous slide. No more complicated than that. So the representation of h of v is you combine the things in the way that they combine. And the rest is a question of getting used to this particular computational scheme. So this is not some sort of gift where I'm telling you something that's just a brilliant idea. If you just write down what the numbers are, you try to make the abstract concrete. You just write down what the numbers are and you see this combines with this combines with this. This is just simply how they combine. So the way the numbers combine to do this computation is you take the dot product of the rows of the matrix with the column representing the input. And the result is the column representing the output. Again, you take the dot product. Remember we defined dot product a couple weeks ago. You take the dot product of the rows of the matrix with the column representing the output. Representing the input, forgive me. And the result is the column representing the output. That's just how they combine. When you put down numbers and you do this combines with, and factor out the 2, 0, it's just how they combine. Okay, so we write this down as a definition, but it isn't a definition that kind of came from nowhere. It's a definition that came from writing down how linear maps act. So if the representation of h of beta 1 is this column and the representation of h of beta n is this column, you write those columns down, first column, second column, third column, write those columns down into a matrix and you call that the representation of the map with respect to the starting and ending bases. And again, I can't overemphasize, there we go, that I just simply took the first column here, wrote it there. First column here, wrote it there. Second column here, wrote it there. Third column there, wrote it there. Because, I don't know, you got to put them together somehow. Putting them together side by side seems like a reasonable thing to do. What's the point? The point is that you get the coefficient of 2, 0 by putting the parts together in this way. You get the coefficient of minus 1, 1 by putting the parts together in this way. And that's all that we're going to write down here. So this is the matrix, and next is going to be the definition of the action of the matrix. Where we go? There we go. The definition of the action of the matrix. The matrix acts on the column in this way. You take the dot product of the first row, dot product of the second row, etc., through dot product of the last row. And it isn't magical. It's because that's just how the parts combine when you write them down. Okay, back we go to the matrix representing the map. You saw there were 3 examples. So the first example is projection from R2 to R2, projection onto the x-axis. I have a starting basis and an ending basis. You have to be told enough to do the problem, so you have to get the starting basis and the ending basis. And again, I picked ones that aren't necessarily straightforward because those are often good first examples. They often illustrate what happens better than straightforward examples. So what do you have to do to find the representation of the map? Why, you figure out what is the action of the map on the first basis element. There it is. What is the action of the map on the second basis element? There it is. So I took the first basis element and projected it. I took the second basis element and projected it. I followed this formula. Once you know what is the action of the map on the first basis element, represent it with respect to the second basis. Represent it with respect to D. And likewise down here. Once you know the action of the map on the second basis element, represent it with respect to the output basis. So you figure out the action and represent with respect to the codomain spaces. Figure out the action and represent with respect to the codomain spaces. You get 2 column vectors because representations are column vectors. You write those down, first column, second column. So you write them down in some organized fashion, and the kind of natural organized fashion is to write them next to each other. So we get 4 numbers there, and those 4 numbers somehow represent this map. What happens if you change the basis? So I took the same map, changed the basis. This time I changed it to an easier one. I've been kind of talking up how a generic one makes a better first example. So my second example is to take an easy basis. Okay, but same thing to do. You figure out what is the projection of the first basis, figure out what is the projection of the second basis vector. Once you've figured out what is the action of the map on each basis vector, you represent those with respect to the second basis. So here 1, 0 is from capital B, 0, 1 is from capital B. Here I'm representing pi of beta 1 with respect to D. I'm representing pi of beta 2 with respect to D. So how do you represent 1, 0 with respect to E2? And you might remember that for the standard basis, every vector represents itself. So 1, 0 represents itself. And again, for the standard basis, D, every vector represents itself, so 0, 0 represents itself. A 0 is always represented by 0, 0. But anyway, 0, 0 represents itself. You take these 2 columns, you write it next to each other, done. Just to do some different map. So here, AB maps it to the real number 2a plus 3b. And again, I'm going to use the standard basis. So where does 1, 0 go? Where does 0, 1 go? So 2a plus 3b, it puts out a 2. 2a plus 3b puts out a 3. Represent those with respect to the codomain spaces. That in this case is the standard basis for the real line. So represent those 2 with respect to the codomain spaces. Everything represents itself. Everything represents itself. Put them next to each other. Okay, so the same 3 steps. Figure out the action of the map on each of the domain basis elements. Represent those with respect, represent the 2 and the 3 in this case, represent those with respect to the codomains basis. And finally, just put them, or but the 2, put them next to each other as vertical vectors, as column vectors, and here they're only 1 column tall, so there's not much columnness to them. And then this says theorem. It says that if you write matrices in the way that we've just been practicing, and you write the representation of an arbitrary vector with respect to the domain basis, then the representation of h of v, the representation of the action of h on v, will be this column vector. And again, I can't overemphasize that it says theorem, but really the definitions are set up so that the theorem has to be true. That is, we organized here, organized the parts in such a way that we just looked how they combined, and they combine in this way. And so that the theorem, in some sense, if the theorem wasn't true, we'd change the representation to make it true in some ways. Okay, so the proof formalizes the example that began the subsection. There is an exercise that asks a person to go through the i's and j's. So, of course, we define then the matrix vector product of an m by n matrix and an n by 1 vector is just the action that we just described here. If you multiply a matrix times a vector, you get the action that we just described. And I didn't make up the matrix vector product and then discover that it represents that's not what we're doing. What we're doing in this class instead is we're writing down linear maps. How do they act? It turns out they act this way, and so this gives us a natural way, a reasonable way to combine matrices and vectors, because we found ourselves combining them. Okay, so the lesson for today, we talked today about how to represent maps with respect to a domain and codomain basis. And the point is to make it be the case that when you take that matrix representation and apply it to the representation of the vector, why you get the representation of h of v. So the important part to remember here is that these definitions are not arbitrary. They're made up by just picking some numbers and seeing where the way the different parts combine, and then the result is just a question of saying, well, we wrote down the information in an organized way. It combines to give you this, and that's what we're going to take for the definition. Okay, of course, when we come back next time, we'll do some more practice with the matrix vector definition that we finished with today. Okay, very good, very good.